Good evening. A warm welcome to ISET webinar on a seismic movement magnitude scale, which is jointly organized by Indian Society of Earthquake Technology, Roorkee chapter, and Department of Earthquake Engineering, IIT Roorkee. This webinar will be delivered by Dr. Ranjit Das. Before I hand over this session to him, I would like to briefly present his short bio. Dr. Ranjit Das is an internationally recognized researcher and industry expert in the areas of earthquake engineering and developer of a new earthquake magnitude scale. Dr. Das is currently working as assistant professor at Universidad Católica del Norte, Chile. He is also a researcher of National Research Center for Integrated Natural Disaster Management, Chile. He received PhD degree in seismology from the Department of Earthquake Engineering, IIT Roorkee. He has experience and expertise in the areas of earthquake size, earthquake catalog, and seismic hazard assessment. He was among the 50 who received the National Doctoral Fellowship from the All India Council for Technical Education in the year 2009. Being a life member of Indian Society of Earthquake Technology, Dr. Das has made 23 peer-reviewed high-impact factor scientific publications. He also made several basic algorithms useful for science and engineering. Dr. Ranjit Das is also serving as an associate editor of world's oldest geophysical journal, Journal of Geophysics. With this brief introduction, I welcome Professor Ranjit Das and request him to make his presentation. Followed by his presentation, there will be panel discussions. Professor Ranjit Das, please, you can share and start the presentation.
Thank you, Professor Jaka, for introducing me. I'll give some, some explanations, some works on our works. That is a seismic moment scale. I will explain how we have done these works and what is the importance of this scale. So I will try to represent with my slides. So I'm now sharing the slides. So this slide is visible?
Yes, yes.
Good afternoon, all of all the participants. So, and good afternoon, sir, Professor Vash and Professor M.L. Sharma, sir, and Professor Jaka. And so, in this seminar, I will present our works, the seismic moment scale. And this is called dash magnitude scale. So before introducing this scale, or before I will explain this, what is the importance of the scale, what is the basic background of the earthquake scales. So I am already Professor Jaka introduced this. I am an assistant professor of Universidad Católica del Chile, also a researcher of Disaster Management Center, which is conducted from Pontificia Universidad Católica del Chile. I am also an associate editor of Journal of Geophysics. So I'm starting my works explain. So yeah. So actually earthquakes occurs all over the wall, all over the walls. So mainly in the flat boundaries, the bigger earthquakes comes. So we and in Himalaya, there are so many big earthquakes comes. So, and this causes casualties, damages to the economy of a country. And therefore, it is important to understand the earthquakes and to build up a earthquake resistant building. So, for designing earthquake resistant building, we have to calculate the hazard, vulnerability, and exposures. So for doing all this type of analysis of earthquake engineering or seismology or any other geophysical So we need to understand the earthquake size. So what is the bigger, what is the amount, what is the how much big the earthquake is. So that is called magnitudes. So therefore earthquake magnitude is very important for any analysis, for doing hazard assessment, risk assessment, or maybe any geophysical studies. Earthquake magnitude is the main parameter to represent the research. So therefore we hammering this part, whether this is an appropriate scale, or whether the existing scales are measuring the earthquakes are appropriate or not. We are doing a rigorous exercise for this magnitudes of earthquake. So this is the scale. Actually, we have published in BSSA. It is a top downloaded paper in 2020. There are 5 papers also. So earthquake size basically determined by magnitudes or by intensity. So magnitudes give you the size of the earthquakes, how much big the earthquake is, and intensity give you also by the intensity you can also measure the earthquake. What is the degree of shaking of the earthquakes at different places. So magnitude is the best for representing the earthquake size, because intensity is decreases with respect to distance. There are many, so earthquakes are classified with earthquake magnitudes. So if we have a bigger earthquake, great earthquakes we call, if it is a magnitude of earthquakes is more than 8, and we call this the measure our large earthquakes if it is coming between 7 and 8. So, and moderate if it is coming in around 5 to 7, and small we call 3 to 5. And the micro earthquakes is called 1 to 3, and ultra micro earthquakes is 1.0. This is a convention given by Hagiwara in 1964. So this is the actual classification on the basis of the magnitudes. If it is bigger than 8, then we call it as a great earthquakes. So there are so many big earthquakes in the planet. Probably in every year there is a big one earthquakes in this planet. So these magnitudes, from the very beginning, so from 1935, this actually earthquake science is very new science. Actually, in 1935, Richter's first developed a mechanism by which one can measure the earthquake size. So that is called local magnitudes. So and also called Richter magnitude scale, which is published in 1935 in BSSA. So this scale basically defined for Southern California to understand how the seismicity of that area. So after in 1 year, then he found that the local scale we have developed. So if an earthquake comes in the bigger area, the longer area, so this actually scale does not satisfy. So then he developed another scale called surface wave magnitudes, that is called MS. But MS also have some limitation because it cannot properly report the deeper earthquakes. So then he developed in 45 after 10 years or 9 years after that, he developed another magnitudes called body waves magnitude. That is, initially it was M capital B, but at present we have M small b. So in this way, the magnitudes are improving or modifying. So after 30 years of Gutenberg developing the body wave magnitudes, Hans Kanamori comes and so told that and suggested that these scales are having some limitation. Then they develop another scale, which is called moment magnitude scale. In 79, it is actually published. Then another scale comes in 1986 in JGR. This is called energy magnitude scale, because many people suggested that only one scale cannot represent the earthquake size properly. So therefore, on the basis of the ground velocity, this energy magnitude scale is developed by Choi and Botwright. So this is energy magnitude. This energy magnitude generally reported by NEIC website. So in 2019, we developed another scale, which is called Dash magnitude scale and represented by MWG, also published in BSSA. So there are some limitations between the different magnitudes. You see this graph for how this moment magnitude, this is a Heaton curves probably in 1986, it has been given to make the correlation between the different magnitudes. So MWC in this graph, there is no saturation, but MB has a saturation, ML has a saturation, M capital B has saturation, MS has also saturation after 8 or 8.2. So, but MW is not saturated. So therefore, after 79, everybody started to apply the MW scale, the moment magnitude scale. So this figure shows that how different magnitudes of earthquake size actually having the limitations. The body waves is called MB and local wave is called ML, and this is MB body waves, this is surface wave. So this all the magnitude scale having some limitation except MW. So yeah. So now I'm trying to say what is Richter scale. So Richter in 1935 first proposed a scale called the Richter scale, and this equation, the scale was given by Richter in 1935 is ML equal to log of A minus log of A naught, where A is the maximum trace amplitude recorded in a standard Wood-Anderson seismogram. That has natural period of 0.8 seconds. And A naught is the zero of the local magnitude, arbitrarily fixed as 0.001. That means at 100 kilometer epicentral distance, you will get this much of amplitudes. So this is the actual Richter scale developed for Southern California. So many developed countries, or Canada or some other developed countries, develop their own scale, local scale. You know, it is important to understand that Richter scale having its own, you know, correction factor for own tectonics. So so Canada having developed their own scales, and other countries also develop, but I think in India still using this Richter scales. So the correction factor has to be improved. So these scales, although we use, but we have to incorporate some correction with this scale so that it can properly give the information of tectonics. So this is developed for Southern California. And how to measure this, how to use this Richter scale when an earthquake comes, a signal goes to seismograms. So this gives us the P waves, and this is the S waves. If we give the difference between the P and S, so we'll get some time interval. So we get 24 seconds. So within the 24 seconds, we find this is the time gaps. And what is the maximum amplitudes? We see this is the maximum amplitude of the signal is 23 mm. So then on this is the graphs given by the Richter. So this is the amplitudes of the earthquake signal, and this is 23. And this is another thing, epicentral distance from the graph we have to calculate. And this is the S minus P time gaps, 23. We have to make a straight line from this point to this point, and then where there is an intersection of the magnitude scale, that is the magnitude by the graphical representation. So and then after that, this Richter also gave the body wave magnitudes. So this after some years, so it is revised with respect to time. So MB equal to log of 10A, a maximum amplitudes with respect to time by divided by time, and some attenuation function of P waves given by the Gutenberg and Richter in his table, and then subtract 3.0. So with this information, maximum amplitude with respect to time, we have to calculate the body waves of a earthquakes. So this is next we are coming to surface wave. Surface wave magnitudes basically give the information of the surface, and it is also initially defined by Gutenberg and Richter in 1936, and then it has modified by different people. In 1962, Vanek et al. Developed another scale called the so Vanek et al. Modified this surface wave magnitudes like with some correction factor. So this scale is used by ISC in a different way, or NEIC in a different way. ISC use the vertical component of the seismograph, or NEIC use the vertical and components with 10 to 60 seconds windows. So, and this A is the maximum horizontal component of any time period, and that is the epicentral distance in the kilometer. So these all, so body waves, surface waves, local magnitudes. Local magnitudes are not reported by ISC or NEIC. So these surface and body waves are reported by international agency ISC and NEIC. So now we are coming to the another scale that is called body moment magnitude scale, because we already said that this scale having limitations, so this does not serve our purpose if a big earthquake comes. So therefore, Hans Kanamori defined another scale that called moment magnitude scale. So in order to understand the moment magnitude scale, we need to understand what is seismic moment. The seismic moment is calculated the shear modulus with the area and this location displacement during the ruptures. With the help of this, we can estimate the seismic moment. Also, we can by the spectral analysis, also we can define the moment from the spectral analysis also. Yeah. So then I'm trying to show you this some moments, seismic moments and fault areas of some important earthquakes. So here it is 1960 Chile earthquakes. It has around length is around 800,000 kilometers and its width around 180 kilometers. So this is the information for different earthquakes of seismic moments and fault ruptures for different earthquakes. So yeah. Now these seismic moments one can estimate from the Harvard website. If give the latitude and longitude, one can easily estimate the one can easily got the seismic moment or different type of magnitude also, MB, MS, and the fault plane information also. So if one give the in the this website globalcmt.org, they will give that asks the latitude and longitude. Once insert this information, you will get the moment of any earthquakes, seismic moment. So this is actually the background about all the earthquakes, how the different magnitudes works for measuring the earthquake size. And now I'm telling about the background of MW scale. So the MW scale basically derived from the surface wave magnitudes. Although it is an equation of 2/3 log of m naught minus 10.7, but the background of this scale is totally dependent on the surface waves, because 2/3 log of m naught minus 10.7. This 2/3 minus 10.7 is coming from the surface waves formulations. So so first, Gutenberg and Richter give a unified magnitudes relation with respect to ms, that is m equal to 2.5.63 m. This is the first equation given by m capital B and ms. This is the for converting this MB and capital MS to one magnitude, that is called unified magnitudes, and they make a relationship between the unified magnitudes and M with these formulations. And this he also derive a formulation between the unified magnitudes and the energy with this. So when this equation 1, if we put in the equation 2, then we will get a equation 3. And this is a very, very famous equation for earthquake engineering. That is log ES is equal to 1.5 ms 11.8. So this equation is derived from this equation 1 and equation 2. So equation 1 is connected between the unified magnitudes and ms, and then the second one is connected to the energy and the unified magnitudes. If we substitute the equation 1 in the equation 2, we will get equation 3. So now what Hanks and Kanamori did, use these equations for entire mechanism is based on these equations. So log ES is equal to 1.5 ms 11.8. So this now what he has for deriving the MW scale, he used this ES is equal to stress drop by modulus, shear modulus into m naught. So and considering this stress drop by shear modulus, is 1 by 2 into 10 to the power 4 into m naught. So this is a constant term. What he considered the stress drop and the shear modulus part makes consider the same. Consider a constant value. So he considered a constant value and put this in this formula. Equation 3, log of energy into surface waves. This famous formula, putting this value of equation 5 in the equation 3. So this equation 5 is energy versus moment, and which is a mechanical formulation that is coming by considering the assumption of constant assumption by stress drop and the shear modulus. So he considered the shear modulus, constant value, also the stress drop a constant value. So then he find another constant value and put this value into this. So then what is interestingly, he find a equation log of m naught is equal to 1.5 m and 16.1. And surprisingly, this equation is also very much similar with this equation of surface waves and log m naught given by some Roorkee and Boro and some peoples. And this equation is also very much similar with the local earthquakes, that is between the moment and the local earthquakes, equation 8. So this equation 6 is very much similar with the Californian earthquakes and the surface wave between the moment. Therefore, we found that this equation is having very good sense. And now he reversed the equation 6. Just reverse the equation 6, bringing in the right hand side 1.5. Then he makes this mw is equal to 2 by 3 log of m naught minus 10.7. So this is the equation given by Hanks Kanamori. And considering the equation 1 and equation 2, putting in equation 3, which is a equation for energy versus magnitude. In this equation, m naught is not the observed seismic moment. This is the actual, it is a moment, but this equation is coming from by putting the substitution value ES is equal to 1 by 2 into 10 to the power 4. So this equation is having a substitution, having not do not have the direct seismic moment values. Also based upon this log of ES is equal to 1.5 ms plus 11.8, and mainly the Southern California regions 1.5 ml plus 16.0. Also the constant stress drop, which is considering for bigger, only considered for the bigger earthquakes, shallow earthquakes. So he finally give these equations and try to correlate with the different earthquakes of Southern California. So here in this table, it shows that this is the M is the earthquakes magnitude, which is derived by the Kanamori formula, M, capital M, only M. And he tried to look at how much different from the MS and ML. Mainly ML is all from Southern California. So he found that it is a very closely connected, this capital M, MS and ML. Similarly, for the bigger earthquakes, he tried to connect with the surface waves magnitudes M and Ms. And he found this capital M that is coming from his Hanks and Kanamori equation and the MS is very good connection for the higher magnitudes. Also for the lower magnitude is very closely connected. Then he suggested to use this equation for the globes, for specifically for bigger earthquakes greater than 7.5. So now we have some problems with these scales. So I will try to say how are the problems in these scales. So this is basically MW is mainly based on surface wave magnitude. Therefore, do not represent the source appropriately. How it is surface wave magnitudes? See, this is ES is equal to MS. This is surface wave magnitudes, completely based on this equation. So this equation is mainly based on surface wave magnitudes. Therefore, do not represent the source appropriately. It is not that only that we are talking about this not appropriately represent the surface wave. Professor Borman and many other people reported that these earthquakes having limitation to represent the source properly. Then development and validation of this scale only cover the Southern California tectonic and does not represent the different tectonic of the globe. If you go back and you see all the earthquakes are coming from the smaller earthquakes are Californian, mainly. Smaller is California and bigger is 7 point more than 485. Then some extent it is from out of southern. Also see the seismic moment and for the some large California earthquakes. So all are Californian earthquakes here in comparisons. So development is also based on these equations and used for the in case of development. It is also used the California earthquakes. This is 1.5 ml is California earthquakes. So this equation also validation is also having the Californian earthquakes. So what we can say, this MW scale only cover the Southern California earthquakes and tectonics. So does not represent the global tectonics. So because if we change the place to place, the tectonics are different. So we will get different equations. So MW scale is valid for bigger earthquakes at global level. More greater than 7.5, it is valid for most of the world earthquakes. In general, in any regional catalog, most of the earthquakes are smaller and intermediate. So therefore, inconsistency definitely caused by due to the MW scale, because MW scale is valid for bigger earthquakes. Professor Hanks and Kanamori also said this is for greater than 7.5 because he validated for greater than 7.5. So less than 7.5, he is consented for the Southern California. So it does not give for smaller and intermediate earthquakes for entire globes. So it is valid for global earthquakes, bigger earthquakes. And MW scale was derived for upper crustal earthquakes and applicable for large earthquakes. So this is derived for upper crustal earthquakes means while if we go back, you will get this equation 4, this stress drop. Stress drop he considered for the upper, and shear modulus is also considered for the upper crust. So shallow earthquakes. So therefore, this it is also applicable for since it is based on surface waves, it is only valid for shallow earthquakes, not for applicable for entire crust, and applicable for large earthquakes. So it is MW scale overestimate the lower earthquake magnitudes and underestimate the bigger earthquake magnitudes, which is reported by many other peoples. Also, we also explain in our different publications. So MW is formulated based on substitution rather than directly observed seismic moment. So what we did, the MW is formulated on the basis of substitution. Substitution means if you go back, we will see this M naught is coming direct. The correction between the ES and M naught is based upon some equations, constant, and this is coming from a substitutions. So if this on equation 3, if we put the equation 4, we substitute the equation 4 in equation 3. So this MW scale is formulated based on substitution, not on the directly observed seismic moment. So there is no correlation between the seismic moment and other magnitudes with the direct observation. They have some substitution of considering some constant values. They develop these scales because the MW scale is derived based on long period surface wave magnitudes. Since it is based on the seismic moment and the surface wave magnitudes, it is not a good estimator for high frequency or strong motion amplitudes measurement, which are useful for potentially shock damage of present earthquakes. So MW scale was derived by substituting a constant term, which I am already talked. That is 5 into 10 to the power minus 5 is equal to sigma 2e, the Gutenberg equation. This it is important to note this stress drop varies generally from a few bars to 125, but he considered some constant value. So this variability of stress drop is significant. Therefore, if we change the stress drop, we will get the different values of this different from the MW scales. So this is another limitations. Consider the constant terms in developing this, this scale, and this also does not have a good statistical agreement with the observed magnitudes. If we see this, but in the development of MW scale, he tried to compare the MS and ML, so observed magnitudes. Whatever the moment magnitude gives, he tried to compare with the MS and ML. So now if we compare this MW scale with MS, MB, ME, we don't find any good correlation between correlation or very good statistical agreement with the MW scale. So now this is an attempt to cover up the limitation of the existing scales, because many people suggested that, yeah, only one scale do not represent the entire earthquake scenario. So there should be some other scales. So we try to think on the direction so that we can at least remove some of the problems of MW scale. So previously the scale was derived on the surface waves, considering the surface wave magnitudes. So now we consider the PUF, first few cycle of the PUFs of the magnitudes. So here is the, we consider the, not the surface waves, for the body wave magnitudes only. So how we derive these scales? We consider the first few cycles of, P waves and consider the observed seismic moment. We also consider the radiated energy of seismic radiated energy, and we consider the global seismicity while we analyze our the results. And then we develop a correlation between the seismic moment also in the first few cycles of P waves. And finally, we come to this MWG equal to log of M0 by 1.36 minus 12.68. This is a rough, how we develop this scale. So I try to find out, now I will try to say how this scale has been developed. So for developing this scale, we consider not the specific, seismicity specific tectonics. We consider entire globe data, seismic moment data. It has considered 25,000 data during the period of 1976 to 2007. Also, we consider the body wave magnitudes around 3 lakhs data and MS magnitudes around 80,000 data from ISC. And also we consider ME 1361 events from NEIC. So we also consider the energy magnitude and energy, radiated energy of 3 directly observed from the instrument. We consider 361 events recorded by Choi and Bootwright. And then we estimate the seismic moment from the energy. And after that, we make a relationships between the moment and the body wave magnitudes. So whatever the magnitudes we collected from the ISC, suppose body wave magnitudes, and correlate with the seismic moment of the GCMT, we found a relationship like this, which is we are considering the saturation up to the 7. But here we, So then see, this is the equation log of M0 equal to 1.36 MB minus 17.24. So now MB has a limit. If a bigger earthquake comes more than 7, it will not give a correct results. So if we can estimate that moment directly from any instruments for the bigger earthquakes, then it is possible to make these magnitudes unsaturated. So then what we will do, what we have done, we just reverse these equations so that directly we get the moment and estimate the magnitudes, which will not, then MB saturation problem will not be there. That idea is just this MB, if we put the directly independent moment and put the independent moment there, then whatever the magnitudes will be there will not be saturated. So this is the concept behind this, how to get from the seismic moment and body wave magnitudes to just reversing the equations. We found that this equation does not saturate it for the bigger earthquakes. Then this functions, this scale is validated with the seismic radiated energy and observed magnitude scales. Once we found this scale is heavily close, very close with the seismic radiated energy and the other observed magnitudes for different parts of the world, then we say this scale can be a proper representation for earthquake size for entire world. So thus I'm showing here, so how this existing scale, moment magnitude scale is not very close to the observed scales. So this is the data set we consider for MB, for MS, for entire globe, not for Southern California. We consider the entire globe. So if we use the scale, this is the scale of Hanks-Kanamori scale. If we consider the scale, then we found this scale is not fitting very well with the for the global seismicity. It may close with the Southern California, but not at all for global seismicity with respect to MS as well as MB. So serious disagreement with the MB as well as MS. So if in case of MS, it is actually, if we go around more than 7.5, it is more or less similar, but before that it is not matching with the existing MS or existing MS with MW. So this figure clearly indicate that the existing MW scale is not very much matched with the surface wave magnitude, also the body wave magnitudes. So this is a critical problem, because development of this scale was based that whatever the magnitudes develop, it represent the other magnitude also. It very close with the other magnitude also. But in case of global scenario, these things has not happened. So we compare with the observed seismic moment. Next, we try to compare with the seismic moment. We have the observed seismic moment data from the GCMT and try to connect from the MB and make a relationships and try to connect with how it is how it is close to the seismic moment. We found the existing scale MW is not also very much close to the seismic moment. If we convert from 1 MB to MB to MW or MB to MWG, this dark black indicates the dash magnitude scale, and the other one is called is from the Hanks and Kanamori. So dash magnitude scale is the black, hard black, so which is passing through the middle, and the other one is not passing through the middle in both the cases. So this shows that this existing scale MW is not also matching with the observed seismic moment, because during the time when it was developed, we do not have sufficient seismic moment. So therefore they developed it from the others, considering some other substitution and assumptions. They give the equation for seismic moment magnitudes, considering based on some constant assumptions. So therefore it is not matching with the observed seismic moment. So now we compare the so this again we saw from the, if we have the log moment, if we have the seismic moment, and try to correlate with the different magnitudes. So if we have the seismic moments we have around 27,000 seismic moments. So from the seismic moments we calculate the our scales, also the Hanks Kanamori scales. We found this both the cases. It is very good closeness in case of MB, also in case of MS, for especially in the range of 25 to 29 seismic moment, or maybe in the sense of MS it is 6 to more than 6. It is very closely connected with the our scale is very closely connected with the MS magnitudes. In case of MB, our scale is very closely connected with less than 5.5 in case of body wave magnitudes. So if we consider that the earthquakes or body wave magnitudes, if it is less than 5.5, if you have a earthquake magnitudes less than 5.5, then you find the moment magnitude which is coming from our scale will be very close to the other magnitudes, that is body wave magnitudes. In case of MS, if we found some surface wave magnitudes more than 6, and then estimate and then compare the moment magnitude scale by Hanks and Kanamori and also us DM scale, then we found that the more than 6, this scale is also give a very close connection, very good agreement in case of MS for bigger earthquakes. So this indicates, and also we compare with the energy magnitudes. So we have some 1361 data, and from the local magnitude seismic moment, we try to connect with, compare with the energy magnitudes what are available in the NEIC data. We found this DM scale, that is the blue one, is very much close with the energy magnitude also. So Next, okay, this scale is very much closely connected with the seismic observed magnitudes. Also, we have 361 seismic radiated events from Choyan Butrai. He independently estimated the energy of 361 events. Then we use these energy events and calculated from the moment, we calculated the energy by both this way, by in our scales, also in Hanks-Kanamori scale. We found this, the DM scale, that is this black one, is very in the middle of all this observed data. So this clearly indicates that this scale is very close to the energy magnitudes also. But this MW scale is not very good agreement in case of energy also. The reason behind this, at that moment, we don't have sufficient data for deriving this, energy. So there was an assumption of some data sets. Therefore, energy magnitudes, in case of comparing energy scales, we found there is a disagreement of MW. So what if so therefore, since this scale is very much closer to the observed energy of 361 observed energy all over the globes, and see, this is a table which indicate that how close this is the MWG, and this is MW. This MWG and MW is estimated from the log of moment, and from this MWG we estimated the ES by using this log ES is equal to 1.5 m into 11.8. Using this equation, we estimated this log energy with using the MWG, also MW. We found this log of ES is very close to the log of ES. So in most of the cases, around 85% data, so we have found this very close to this energy, these scales. So then we found we make some statistical test. So whether this MWG scales is actually statistically valid or not. We found that we reject the null hypothesis. This MWG is the mean of the MW. We calculated the moment by using this. We calculated the MWG from the moment, also MWG from the moment, and see whether there is a difference between these two or not, is from the mean and variances. Then we reject the null hypothesis that this is the same. We reject that hypothesis. So does it in this way it is statistically valid. This MW scale is significantly vary from MW scale, mainly in the lower and intermediate magnitude range. So if we now compare some bigger earthquakes in case of bigger earthquakes all over the world. So if we see that Tohoku earthquake in 11 March 2011, it gives 9.1 1 in MW scale and 9.2 in MWG scales. So there is the 0.1 difference in the bigger earthquakes. If we go ahead beyond that, these differences will be more. So in the intermediate steps, it is also 0.1, but in case of 8.8 magnitudes, if the MW is 8.8, but our case is also 8.8. But in the higher, that was 9.1 is reported 9.1, we reported 9.2. So if we see this Tohoku earthquakes, which is 9.1, is devastating a lot. But our scale represent much more better than this scale because it was a huge devastations. In case of smaller earthquakes, if you say the intermediate earthquakes, the 6.5 San Francisco earthquakes, MW give 6.5 and we give 6.3. So in Dhikya-Juli earthquakes, it also gives 6.0, we provide 5.7. So also, if we give the Tezpur earthquakes, it is 4.3. In MW, it is 4.7, we provide 4.3. So there is a difference, significant difference in case of smaller earthquakes. And in the intermediate earthquakes, we also having some differences up to 0.2, but in the bigger earthquakes also we have a difference of 0.1. So remember, these differences are significant because 10 times it will be 32, 1 magnitude scale change, it will give 32 times. And even this scale represent a better terms, better representation of the energy. Therefore, it has much more sense. Also consider the global seismicity, not the Southern Californian seismicity. So MW scale based on Southern California seismicity, but MWG based on global seismicity. So here we consider the global tectonics, not the only Southern California tectonics. So MWG is a better representation of energy than MW. So this this scale developed scales may perhaps will better connects the source process in a better way, because it is developed from the first few cycles of P wave. Because from the first few cycles of P waves, so that is the body wave magnitude, so it represents the source in a better way as compared to the MW. So this DM scale, that is MW, is expected to relate more closely with both high and low frequency ground motion, because it is a function of both MB and M0. Because MB, the 1.36 by 12.68 minus 12.68, the MWG scale is connected with the MB, so which is first few cycle of P waves. The formulation, let me go back. The formulation, this formula 1.36 log of M0 by 1.36 minus 12.68, it is connected with the MB, So this is this 1.36 minus 74, this is a function of MB, also function of moment. So this function of both M and B, so therefore it will represent, it is related more closely with both high and low frequency ground motions. So it is also useful for rapid determination of seismic moment from emergency purpose, but not for higher earthquakes. So now we have just, for some tutorial, we have just tried to find out how it is different in the magnitude conversions. So we find it is very impact in case of conversion also. In case of smaller earthquakes, there is a difference between these scales, MWG and MW.4. And in the bigger earthquakes also, we get some, some type of some variation up to 0.4 in case of 9. In case of MS to MW conversions, if we convert the MS to MW or MS to MWG, there will be a difference 0.4. And if we convert MB to MW and MB to MWG, then there is a difference between 0.4. So this analysis will influence on the seismicity parameters. So we find out how this seismicity parameter vary with respect to seismicity parameter vary on using the MW or MWG scales. We found the B value will change around 25%, A value will be changed 15%, and MC will be changed 20%. This is a case study for Northeast India data. It may vary with respect to the different region. So now why this scale should be used? I think this is the best magnitude scale for measuring all over the overall the earthquake size, from the smaller, intermediate, and bigger. All the earthquakes can be measured, not for the bigger earthquakes. There is no any not for the bigger earthquakes only. So it is the best measure, single measure of overall earthquake size, and it is the best representation of energy, because we have used the global earthquakes, so many big global earthquakes. In terms of energy, we found these earthquakes are very much, this magnitude scale is very much closely connected with the energy. And it is also based on global seismicity, because we have represent the global earthquake data. So, and this MWG scale is also applicable for crust and entire magnitude range. Entire crust means it is also cover the shallow and the deeper earthquakes also. And magnitudes means all the small, intermediate, bigger earthquakes. This scale is applicable, whereas MW is only applicable for shallow and the bigger earthquakes. It fills the gap of long period and short periods, because this scale is covering, consider the first few cycle of P waves, also consider the moment, seismic moment. So seismic, therefore it consider the long period, also short period. So MW scale remove the constancy problem of MW. So in MW preparation, there is a constant values was put before developing these scales. So this problem will be not there in this scale. So it is does not saturated, but this same thing it is happening with the MW scale also will not saturated. This scale will also not be saturated. So it can be estimated from the geological observations. It can be tied to plate motions and recurrence relations. So this much is from our side for representation of earthquake magnitudes. Thank you.
Thank you, Dr. Ranjit Das, for making such a very interesting and comprehensive presentation. And like your presentation and research is giving us hope and encouragement to all of us to look into the basics. Very often we feel that most of the things have been already done and fields are saturated. But through your research, you have shown to all of us one can look into the basic things which we normally take it granted and take it their standard, but you have shown very nicely how one can further improve the existing ones. And I know your discussions sometime when you were here in Roorkee, that the challenge that you faced to publish your research because you are contradicting the well established, well accepted theories. So we are very proud of you, and I'm very happy to inform all our delegates that Dr. Ranjit Das has done PhD from our Department of Earthquake Engineering, IIT Roorkee, under the guidance of Professor M.L. Sharma and Professor H.R. Vasan. In fact, they will be going to be our panelists now. And before we start our panel discussions, I would like to brief our panelists so that you can have effective interactions with our panelists. As I mentioned, our panelists are going to be Professor H.R. Vasan and Professor M.L. Sharma, along with Dr. Ranjit Das. I'm just briefing to Professor H.R. Vasan. Professor Vasan is former emeritus fellow, ex-professor and head Department of Earthquake Engineering, IIT Roorkee. He is also a former president of Indian Society of Earthquake Technology. He has teaching experience 40 years and research professional experience over 45 years. He has successfully guided 6 PhDs and 26 MTech dissertations and published over 85 research papers in 3-4 international journals and conferences. He authored 1 book and 2 book chapters. He was awarded ISET Life Fellowship, and he is also life member of several other societies. His specialization include in seismology, seismic hazard and risk assessment, seismic networks, regression relations, and pattern recognition. He had the honor of being the founder organizing chairman JAM 2004 for all IITs and chairman JAM 2005 for IIT Roorkee. Brief introduction, I welcome Professor H.R. Vasan. And our other panelist is Professor M.L. Sharma. He is the professor at Department of Earthquake Engineering, Institute of Technology, Roorkee, India, with over 35 years of experience in teaching and consultancy. Sharma has rendered expert advice to more than 500 engineering sites regarding seismic hazard and risk assessment. His long association with strong ground motion program of Department of Sciences has resulted in the development of ground motion prediction solutions for Himalaya. He initiated the earthquake early warning system approach for disaster mitigation and management in India. Based on his contributions towards disaster mitigation, with the ACE ARIA IITR Disaster Prevention Award in the year 2012. He was president of Indian Society of Earthquake Technology during 2015 to 2019 and head Department of Earthquake during 2012 to 2016. With brief introduction, now I invite our panelists, Professor H.R. Vasan and Professor ML Sharma, along with Dr. Ranjit Das. Welcome, sir. Welcome you all. Go. So I request our panelists to make initial remarks so that delegates can take part in the discussions.
Before I request Professor Vasan to initiate the discussions, let me tell that I am a student of Professor Vasan and Ranjit Das is a student of both of us. So that's a great opportunity to discuss with the guide and the student both this time. Professor Vasan may initiate.
Hello, good afternoon, everyone.
Good afternoon, sir.
We have just listened to a very interesting talk by Dr. Ranjit. Now, we all know that earthquake phenomena is a very complex phenomena, and it has variations due to its occurrence patterns in terms of size, distance, depth, source type, rupture, and so there are different occurrence patterns are there. And then after the occurrence, then you have the observational part is there, and there are a lot of different. I hope my voice is okay, is audible.
Yes, sir. Please continue, sir.
Okay, then it comes the observational differences. So one has to observe for the amplitudes, its vibrations, and we use so many instruments. We measure it.
I think Udit Srivastav has to mute himself. Yes, done.
So then there are observational differences are there in terms of the number of different instruments being used at different distances being measured, etc. So in order to faithfully represent the complex phenomena variations and the observational differences, we all know that one magnitude scale is not sufficient, and that's why more than one magnitude scales have been devised, invented, and they proposed. And as has been explained, I will not go into detail, the ML magnitude, MB magnitude, MS magnitude, and then MW magnitude. So this MW magnitude, although it's a better and representation, and it's an improvement over the earlier known ML, MB, and MS magnitudes. But as has been shown by Dr. Ranjit, that MW has been from the substitution process of the MS magnitude and the energy, and so, and the log of M naught relation with the energy and the MS. So with these substitutions, Hansen Kanamori proposed a new scale in terms of log of M naught, not in terms of the amplitudes. So which definitely is an improvement over the earlier scale. It removes some of the problems of saturation and other things. But since MW has been tied to the surface wave magnitude MS, which is tied to ES, so the limitations of that surface wave magnitude and those relations, they naturally come to MW also. So MW, although there is an improved scale, but it also got some limitations because it was derived from the relations of MS with log of M naught and MS with energy. So seeing those, in order to further improve and remove those bias coming due to the basic MS magnitude in MW, so this new scale MW has been proposed, and as has been explained, that it is based on the empirical relations derived using large number of seismic moment observations, large number of energy events observations, and these observations are taken not from one region, from all over the globe, representing different tectonics, representing different depths and everything, and different regions are there. And based on the observed large number of earthquakes data in terms of seismic moment, energy, and like that, so MW has been proposed. And so this MWG, since it is based on the observed values of the seismic moments and the energy of small, intermediate, and large magnitude earthquakes, it has been shown, and as is expected, it is an improvement over the MW scale, which was just tied to the MS scale, and those relations is there. So as he has also shown that for very large earthquakes, MWG value is higher than the MW value, but for smaller earthquakes, lower earthquakes, MWG value is lower than MW. So MW gives an overestimate for, there is a cutoff threshold value that is around 7.9 or 8.0. For all earthquakes more than equal to 8 and above, MWG will be higher by 0.1 or 0.2, but all earthquakes lower than 8.0, 7.9 or below, so MW will give a higher estimate by 0.1 or 0.2 as compared to MWG. So for larger earthquakes, MWG is a more realistic estimates, and also it represents well and removes the bias for the lower and intermediate magnitude also. And so MWG should be preferred over MW in calculation of seismic hazard estimates and other seismological studies. So these are my opening remarks for this. Thank you.
Thank you, sir. Professor Anbazgan is raising hand. So before we go for that, very quick comment of mine. There were two things which Ranjit has done. One was to look into the regression analysis part, where one of the dependent parameter was treated as independent parameter. So that was one of the things. What I mean by this is that the dependent parameters are always taken as uncorrelated from the dependent parameter, and they are taken from the observed data. But here he has taken that as a constant. So it was a conflict of dependent and independent parameter while doing the regression. That was number one. The other is the constant was not considering the physical process involved in this, because every area, every region is having a different kind of stress regime, and it depends on that stress regime that the stress drops behavior comes out to be different for different earthquake processes. So that he has not considered. So these are the two comments while making this new scale. The third is that Ranjit, can you do some work on that, because we are taking only the few cycles of primary wave,
Yes,
P waves. Can you change it or rename it to the signatures of the source taken into consideration in terms of primary waves to define the magnitude? Because unless you take the whole signature of P wave or the primary wave to give the, I mean, you are giving the higher magnitudes also. So that signature part should also be considered in this. So your comment on this, and then we'll go to Professor Anbazgan and then to Dr. Seismic.
Yes, sir. This we can look in the future. In the future, we can say.
Yes, we have to take the signature, the full signature of this, not few cycles, so that the whole, I mean, the energy release, the full rupture process has taken place, and then we say the magnitude estimation. Yes, Professor Anbazgan.
Good evening to all of you. So it's a wonderful presentation. So I'm really happy that our people surface in the global level scale of contribution in the moment magnitude. So I do have few, the clarification. So in the figure number, slide number 15. Das, can you go to the slide number?
Yes.
Yeah, please share the screen.
Yeah, so this is the screen, sir.
No, you have not shared it yet. You have to again share it.
Yeah. Share how to?
Down in the bottom, you must be looking at a green button.
Yeah. Is it shared now?
Yes. Yes.
Okay.
So next slide. Next. Yeah. So here actually the ES and the MW relations are predominantly used for the old MW scale, which you are well highlighted. And you also highlighted that the stress stop and the stiffness plays a significant role, okay, where the conversions are happening. Okay, so did you study the effect of this stress stop and then the stiffness variation, how it affects these two parameters?
Not yet. These things actually I have not further. This we can study these things as stiffness parameter variation. These things I have not studied still.
Okay. The second actually you are well highlighted about the 16 and 16.1. So this 10.7 is just a conversion, or I was not getting that point actually. Maybe I missed.
10.7 basically coming from this, the substitutions of this equation 1 and equation 2.
Basically, mathematical jugglery. No, nothing new in this. That's just.
No, actually, if you look at the equation 6 and 8, okay, even 7. So these are all kind of the similar kind of parameters. So the 10.1 is only to take care of the movement of the unit conversion, or
yes.
But in that case, why the other parameters are not affected by the unit conversion?
Sorry, it is actually
no,
here.
2 by 3rd, for example, 1.5 should also be affected by the unit conversion, no?
Actually, this is a unique conversion of M, and I just giving the background how this log ES is equal to 1.5 ms plus 11 point it is derived. Equation 1 is given by Richter, equation 2 is also given by Richter, and what he did is substitute the equation 1 to equation 2 to get a relationship between the energy and the magnitudes, and he got the equation 3. So this is now he considered the base equation for representing the energy with respect to the magnitudes. And then he substitutes some values on this equation to get to remove the answer, remove this unsaturation problem of MS, just like equation 4.
No.
Okay.
The question Professor Baskin is asking whether this equation 9 is just the reproduction of equation 6 or not. I mean, just the
yeah. It just reverse
taking place, and that's it. Nothing new.
Yeah.
So that's good. So next on my observation on this MB and some clarification. So generally this MBs like the P waves are predominantly affected by the water table 2. Okay. So when we convert energy, basically you are explained well here when you talk about MS and the energy relation. But when you talk about the MB and the energy relation, so do you also use similar kind of things, or it is each earthquake energy has been estimated some other way using the waveform is considered, or empirical reflections is used?
We consider the independent earthquakes which is developed from the velocity, ground velocity. Consider that energy for.
Okay, so energy you are estimated from the ground velocity.
From the ground velocity.
So which is not any empirical relation.
No, it is basically a independent data.
And
Okay, so when you talk about this magnitude, so as you have shown all the global data, so the magnitude and the global data what you are showing, actually this data may be recorded with amplification, without amplification kind of things. So does it take care of all those things, or only the raw data has been used?
No, actually amplification informations I have not used. The raw data I use just the velocity and this information I just used.
But that is basically also the function of the seismic site classification at a particular location, no? Because your waves are amplified and the energies are different
Yes,
because
I
of
would
the
like to come
modification
in.
of the soil.
I would like to come in for this.
Yes,
That is basically the difference between a seismological station and a strong ground motion station. A strong ground motion station is just placed at the surface, and there you get the site amplifications and all that. But for seismological stations, you search those very remote sites on hard rock, and without hard rock, you are not placing these seismological stations. So the local site effects, generally they don't change the values, because we search for putting the broadbands and the short, even the short periods on hard rocks only. And if that is not available, then we excavate and go 1 meter, 2 meter, 5 meters down to place the seismometer. So I mean, that is the difference between seismometer placing and the accelerometer placing. When you place the accelerometer, you place it on the surface, and then you correct for the site characterization. But in case of pure seismology, observational seismology, these stations are generally on the similar kind of rock strata.
Yes, sir. I appreciate your, the explanation. But as you know that most of the stations they keep on rock, or they put a concrete bed and keep on that. So as you said that 1 meter, 2 meter. Well, very few places they define a station as a rock station, and most of the place they write only the kind of the details what is mentioned. Even in the Indian stations, North India particularly under your control, and then Roorkee places, and many stations are just kept on the concreting some soil place, and then the stations are kept are
Yes,
the
but
boulders kind of
this
thing.
kind of data is generally coming from observatories.
Okay, so you say that it is rock data completely.
Yes. I mean that kind of corrections are not done in seismological processing. That's what I mean.
Okay, sir. Thank you very much, sir. That's all from my side.
Well, may I
Thank you
add
very
that these databases of NEIC, etc., they use the data from WWSSN stations and the international stations which are linked as per some specifications, and those observatories are very international standard observatories, and their noise levels are so low, are kept, and only then, so these amplification factors are do not enter into that.
Yes.
my last question: how many data of Indian data gone into this kind of equations?
Ranjit?
Indian data actually I have to check, because I have not seen that it is a global data total. Probably maybe 1 or 2 it comes.
Okay,
it's not
so
much
if you
more,
put percentage,
because
it's 0, 1, 0, 2, something like that.
Yeah, 1 or 2
Less
is
than
coming.
that.
It is not
Less than that.
Yeah, not because we cover the whole world, so it is not coming from much more from India.
Okay, sir. Anyway, it's an excellent presentation, Das. So I hope you remember when you visited Earth Science, we had some interaction.
Yes, sir. Yeah.
Okay. Thank you very much. Yeah.
Okay,
So,
Dr. Sejal, your question, please.
Sir, before that, can I just add one point, sir? Just related to the discussion. Actually, I am unable to raise my hand being the host. Just one point, sir, quickly.
Yes.
I think Dr. Ranjit Das is using the P wave. Normally, P wave is not much affected by the local side effects. Just to add.
Yes, that's also the reason. Yes. Yes, Sejal, please.
Sir, how is this going to affect a normal designer like me? Like, I'm asking about how in the relaxed design.
Your sound is not so clear. I'm unable to understand. Ranjit, are you getting the question?
No, sir. Actually, I'm not having this schedule. Can you please actually clear this? Actually, I'm not able to hear actually properly. I'm not getting it properly. Please.
You can write in the chat box, and I can reproduce that. No problem.
Yeah, please.
Yes, Dr. Harish Thakur.
Hello, am I audible?
Yes.
Yeah, you are absolutely.
Sir, I have only one question. Like the diagrams that you have plotted in log m naught versus m.
Yeah.
So those are straight lines, but we can see like those plotted data is in drop shape, like elongated these on 27th slide, 27th.
27, right?
Yes, 27th and 26th. So
Yeah.
my question is like, did you use like linear regression or non-linear regression? Because from but
Yeah, this is a complete, actually the thing is from the very beginning the earthquake scales are based on linear regressions.
yes, sir.
So local scale, body waves, surface waves, everything. So therefore we go for the linear regressions only.
But you can observe the trend here, like it is non-linear curve will fit better on this data, or like this can be studied.
Actually, there is actually we are not concentrated much more on the fitting, how much fitting in the total data sets. If you see in this figure 27, this is a good fitting up to 6 or 5.5 from 4.0 to 5.5 in case of figure A, 27 figure A.
Yes,
It
sir.
is a good fitting the 4 to 5.5. But if you for the bigger earthquakes, if you consider more than 5.5, it is good for matching with the 5.5 to above in case of MS B figure B. See
Yes,
this. So therefore, it overall range it completely matching. It is not connected because small earthquakes are very much useful for body waves, can give a good information for the body. Small earthquakes less than 5.5, the bigger earthquakes, intermediate earthquakes more than 5.5 to 7, 8, the surface wave give you the more information. So in case of 5.5 and above and 5.5 and below, so both the ranges in both the scales, both the figures, these scales are appropriately fitting.
Ranjit, it will be good if you can explain to the audience this, what is the count 15 to 32, the blue one.
It is the number of dots. How many dots are bigger earthquakes? The dots are number of dot count. How much between 15 to 20? That is the number of bigger earthquakes. Or how many bigger earthquakes? Because it is not possible to say one over. It is because of overlapping.
It means
So,
one blue point is
yeah.
representing around 15 to 32 counts.
Yes, sir. Yeah. This is coming in that range, and this is because overlapping for the problem. So we have to give the counts. How much bigger?
Thank you. Olympa, Baru, you want to ask something?
Yes, first of all, good evening, Professor Watson, Professor Sharma, and Professor Japka. It's really nice to see my professors after such a long time. So, Dr. Ranjit Das, I am Dr. Olympa Boro from Department of Civil Engineering, NIT Silchar. So I have two questions. First of all, my first question is, how did you identify the first cycles of the P wave? And my second question is, on slide number 24, you had given an equation, and also on slide number 23, you had given an equation. You said that on slide 24 that because of this equation, this scale does not saturate. So could you just explain to me how you made sure that the saturation did not happen?
Actually, yeah. So for how we estimate the first few cycles of P waves, if we consider the less than 3 seconds in the seismic signal, then if I try to find out what is the maximum amplitude of those before the less than 3 seconds, before 3 seconds. So pick up that. That is the things.
Okay. And
second one?
Yes, on slide 24, could you please go to slide 24?
Yeah, please.
24.
Yeah.
So point number 6, at the end, you have written that which does not saturate. Your scale, you're saying that it does not saturate. So could you please explain how did you make sure that it does not saturate?
Because if we estimate for the bigger earthquakes, because MS saturate means it goes 8.2, before 8.2, it is not giving it does not increases the value. If we improve this, the value of moment, you will not get the improved value of M. then it is saturated. At a particular point, it is saturated, it is not improving. So, but here, if you put the value of moment, increasing value of moment, you will not stop, it will improve.
Yeah, that was seen when a magnitude of 9.1 gave MWG as 9.2.
Yeah,
Yes.
yeah.
So you can see that that's the best example to show that.
Yes.
Yeah, yes.
Oh,
It
thank
will be, yeah. So it is not changing.
So if there are any other questions, we can take
And
them up.
further, one can see from the graph also that this line doesn't bend. If the scale is saturating at some end, then this like ML, MS, and MS, then for higher
Yes.
magnitude, this slopes tries to flatten out and becomes towards the horizontal. So that doesn't happen in this MWG. So that's why from the graph also one can see it doesn't saturate.
Yes, sir.
So,
I want to
because time
sir,
is
I want to,
also, yes.
I want to clear one thing.
Yes.
So that even though this here, our intention is not to make a good curve fitting in the data set of body wave or moment or MS to M naught. So our target is the body wave range, that is the 4 less than 5, and MS range, which is more than 5.5 above, it should be perfectly fitting. So that is what we are testing. These figures, one can assume, oh, these are not good fitting. We are not checking the best fitting line here. We're just trying to find out how much it is applicable range mein ye kitna match ho raha hai. That is the what we are trying to find out.
Okay, so because the time is running fast, and before we close this and go to Professor Ravi, I would just like to have one comment that on another front, our team led by Dr. Das is fighting for and guided by Professor Vasan is fighting for the non-linear analysis that
Magnitude conversion.
Yes, Ranjit will tell. And we are facing a lot of problem from those who have been using those methods for a long time, but there were mistakes. So these things happens between the groups and between the regions and between countries and maybe 2-3 parts of the world. So I may request all the audience that this is one of the finest thing which Ranjit has given, this MWG scale, and I respect it, and we request you to kindly make use of this so that people start using this outside also. People have doing this. It is the most downloaded paper, and therefore I request all of you who are here as audience to kindly start using MWG DAS scale. Thank you very much. And
I am also
yes,
requesting
Professor Ravi, all from us for you.
Thank you, sir. Thank you, sir, for nicely managing the panel discussions. And I also thank Professor H.R. Vasan, sir, for nicely giving the expert summary of the entire work. And also on behalf of ISET and the Department of Earthquake Engineering, IIT Roorkee, I would like to thank our today's speaker, Dr. Ranjit Das. He has really come up with a new scale, and which is really wonderful and astonishing work. And hope we will all start using this. And at the end, I would like to also thank our delegates for participating in the panel discussions and attending this webinar. And also like to thank our ISET staff and students, particularly Mr. Saikat, who helped me in arranging this webinar online. Thank you, one and all.
Thank you so much.
Thank you.
Thank you so much for being